Hello everyone. First and foremost, I would like to thank Department of Physics, NAMCHI Government College and Sikkim University to provide this platform to make an assignment on the topic Logic Gates by Dr. C.P. Khatiwada sir for the partial fulfillment of BSc third semester June to December 2020. This video carries 25 marks or sessional B examination. So let me introduce myself. My name is ARUN KUMAR MAHATO and my roll number is 19NS0152 and my topic for the assignment is logic gates. So let us see what are logic gates. So as the name indicates that these are similar to our normal gates which allow or deny someone. For example, if we allow or deny anyone entering room, we use gates or doors. So in the same way, to allow or deny any digital signals, we use logic gates. For example, if we are allowing any digital signal, logic gates each allow the specific combinations of input signals. Generally, these logic gates are used to define a Boolean expression. Whatever output of logic gate is there, these are called Boolean expression. So these are the basic building blocks of any digital circuit design. So if you want to design any digital circuit, it is not possible without logic gates. So now let us see the types of gates and the major types of gates. So logic gates, the basic logic gates are number 1 AND gate, number 2 OR gate, and number 3 is NOT gate. So these three are the basic type of gates, and there are two types of universal gates. Universal gates, that is number 1 is NAND gate and number 2 is NOR gate. These two gates are called the universal gates because any other gates can be realized by using these two gates. And the other types of gates are number 1 XOR gate and number 2 XNOR gate. So these are the other type of gates. So now let us see the logical symbols for all these gates. Now let us see the logic symbols. Now logic symbol for number 1 AND gate. So this is A, B, this is Y. So this is the logic symbol for AND gate, and this A and B are the inputs and Y is the output. Any logic gates except for the NOT gate, they may have 1, 2 or more than 2 inputs but can have only one output, where this A and B are input and Y is the output. So we can say input as excitation and output as response. So we can say all gates can have more than 2 excitations but can have only one response. And number 2 is OR gate. OR gate. The logic symbol for OR gate is like this. This is Y, this is A, this is B. Now number 3 is the NOT gate. So NOT gate. So NOT gate only gives the complement of the input. So this is NOT gate. It gives Y is equal to A bar. So it gives the complement of the input. The output is the complement of input. Now number 4 is any AND gate, and the logic symbol for any AND gate is like this. This is A and B are the inputs, Y is the output. So any AND gate is similar to A AND gate, but it is only with a NOT. Number, let us see NOR gate. So this is NOR gate. So NOR gate is also similar to the OR gate, but only with a NOT. So this is the NOT. So we can observe that all the gates have one, two or more than two inputs, but has only one output. And number 6 is the XOR gate. The logic symbol for XOR gate is this. So this is Y, A and B the inputs, that is the output. And number 7 is the last gate, that is the XNOR gate. XNOR gate. This is Y, this is A, this is B. So XOR gate is nothing but it is the complement for XNOR gate is nothing but it is the complement for XOR gate. So whatever be the output of the XOR gate, so the output of the XNOR gate will be the complement of XOR gate. So now let us move to the truth table for all the gates. Truth table. Now truth table. So we know that truth table is going to provide the input and output relation. So truth table will define what may be the output of logic gates for particular combination. So truth table always contains columns which is having inputs and outputs. So this will be the inputs and this is the column for the output. So it may have two or more than two input but has only one output. So for like how many combinations we can have here in the truth table, that is we can have 2 to the power n combination where n is the number of input bits. We can have 2 to the power n number of combinations in the truth table. For example, if we are taking an 2 input AND gate, then the number of input is 2, so 2 to the power n, so which is 2 to the power 2, which is 4. So we can have 4 combination for 2 input logic gate. Similarly, if we are having 3 input logic gate, so we can have 2 to the power 3, which is 8 combinations in the truth table. So now let us see the timing diagram. Timing diagram for the different types of logic gates. So what are timing diagrams? So timing diagrams are nothing but diagrammatic representation of input and output. So timing diagrams are nothing but it is the diagrammatic representation of input and output. For example, it is represented 0 is represented as low. So it may be represented like this. So this is low, and high or 1 is represented in these lines. 1. So let us take an example like suppose there is T1 is 0, T2 is 1 and T3 is 0. So timing diagram for this will be T1, T2, T3. it is for A. So T1 is 0, so 0. T1 is high, so 1, it is high. T3 is 0, which is low. So it is 0, 1, 0. So this is the timing diagram. Now this is the logical statement. So we can say that 1 as high, positive, on, close, conducting, right, true or yes, and 0 is low, negative, off, open, non-conducting, wrong, false or no. So now let us see A and D gate in detail. A and D gate in details. So A and D gate is nothing but it is the logical multiplication. Whatever we are providing for A and D gate, those are going to be multiply, and we are getting output based on the logical multiplication. So A and D gate, it is nothing but the logical multiplication. So suppose this is A and B and the output is Y. The Boolean expression for this is A dot B is equal to Y. Now truth table for A and D gate. Truth table for A and D gate: input, output. So we can have 2 or more input but only 1 output. So let us consider 2 inputs and 1 output, that is Y. So the combinations can be 0 0, 0 1, 1 0, 1 1. So for 0 0 it is simply the logical multiplication. So 0 dot 0 is 0, 0 dot 1 is 0, 1 dot 0 is 0, 1 dot 1 is 1. So this is the truth table for the A and D gate. And let us draw the timing diagram for this gate. So timing diagram. So the timing diagram, so it is for 2 input A and D gate. So let us consider the timing, this as T1, this as T2, this as T3, and this as T4. So this will be T1, T2, T3, T4. So A, as we can say that A is 0 0 1 1 or low low high high. So it is 0 0, 1 is high, another one is also high. So it is 0 0 1 1. For B, we can see it is low high low high. So which is low high low high. So it is 0 1 0 1. For the Y, which is the response, it is 0 0 0 1. So it is low 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 high. It is 0 0 0 1. So now let us see the circuit diagram for the A and D gate. Circuit diagram. Circuit diagram for A and D gate. So it is so these are the diodes. This is D1, this is D2 diode, and these 2 diodes are connected with resistor R and of VCC, and this is the output Y. So this circuit is internally integrated to the logic gate to perform specific logical multiplication. Here the 2 diodes, which are D1 and D2, are connected to VCC through resistor R. And when these 2 diodes are short circuited is the open. Short circuited, which is on or open. whenever these two diodes are on, which means the anode voltage is higher than the cathode voltage, that is particular diode is on, that is short circuited. So we will be see when the diodes are, if anode voltage is high and cathode voltage is low. Suppose A is 0, B is also 0. If both the inputs are low, suppose both the inputs are low, so 0, it is 0, 0. So these are connected to resistor and VCC resistor. The output will be Y is equal to 0. Now again, considering A is equal to 0 and B is equal to 1, that is A is high and B is low. So A is high, so which means 0, and 1 is, it is open circuited, and this is output. So here the Y is also 0. Again, considering A is 1 and B is 0. A is 1 and B is 0, it means 1, it is open, 0. This is the output. Again the Y will be 0. Suppose both are high, A and B are high, then Y both are open circuited. This is output and VCC. So Y will be 0. So this Y is 1. So we can see that this matches the truth table. So now let us see the OR gate. OR gate. Generally, OR gate will perform the logical addition, that is addition of input signals. The Boolean expression for OR gate, it gives logical addition. The OR gate performs the logical addition, and OR gate can have n number of inputs, like for n input OR gate, it may be represented like this. This is Y. It can have n number of input, B and n number of input. And the truth table. Let us see the truth table for OR gate. Input, output, A, B. Let us see the truth table for 2 input OR gate. So the combinations are 0, 0, 0, 1, 1, 0, 1, 1. So it performs the logical addition. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is also 1. So this is the truth table for the OR gate. Now, following with the timing diagram for the OR gate. Timing diagram for the OR gate. So the timing diagrams for OR gate is this is T1, this is T2, this is T3, this is T4. So timing diagram T1, T2, T3, T4. For A it is 0, 0, 1, 1. So 0, 0, 1, 1. For B it is 0, 1, 0, 1. So 0, 1, 0, 1, 0, 1, 0, 1. And for Y it is 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. That is low, high, high, high. So this is the timing diagram and the circuit diagram for OR gate. So let us see the circuit diagram for OR gate. So it is also connected to the two diodes, that is like this. B is also connected with diode. This is D1 diode, this is D2 diode. So it is connected with a resistor R and it is grounded in the ground. And this is the output Y. So this is the circuit diagram for the OR gate. So as we can see that it is internally integrated inside the logic gate. So this is the OR gate and the circuit diagram is internally integrated, and these two are the diodes and it is connected with a resistor which is grounded. So now we will be, so now let us whenever these diodes are, that is, so whenever these diodes are on, that is whenever the anode voltage is higher than the cathode voltage, then these diodes are going to be on, that is short circuited. For example, if we consider A equal to 0 and B is equal to 0, so diode is off because anode voltage is lower than cathode voltage equal to ground. Suppose A is 0 and B is 0, then diode will be off because anode voltage and cathode voltage are equal, and which is equal to the ground voltage. So it will be 0 and this is also 0. This is the output. It is connected with a resistor and it is grounded. So Y is equal to 0. And if we consider again A is 0 and B is 1, that is A is low and B is high. For this Y is 0. For this A is 0. So which means it is open for 1. This is open circuited. So for this the Y is equal to 1. Again if we consider for number 3, A is 1 and B is 0, then this is 1 and B is 0. Resistor, it is grounded. So this is the open output, so Y is equal to 1. For number 4, again if we take example like A is 1 and B is 1, then Y will be equal to 1. And this matches the truth table. So hence we can say that the circuit diagram here works perfectly. Now let us see the NOT gate. NOT gate. So it is going to provide the complement output for the input. The NOT gate provides the complement input for the output. Suppose the input is A, then the output will be its complement, that is A bar. For example, if we provide the input as 1 and we'll get the output as 0. Suppose the input is 0, the output will be 1. Similarly, if it is off, it will give on. Suppose it is on, it will give off output. The truth table for the NOT gate is the only gate which has only one input and has only one output. That is, it has only one input and has only one output. So suppose the input is 1, 0, it will give 1, and if it is 1, it will give 0. The timing diagram for this will be the timing diagram for the NOT gate. So suppose this is T1 at time interval T1, this is at time interval T2. So T1, T2. This is for A. So it is 0 1 0 1. For Y it is 1 0. So this is the timing diagram for the NOT gate. So now let us see the NAND gate. NAND gate. NAND gate. Generally we know about AND gate that will provide logical multiplication. Whatever logical multiplication is done by AND gate, it is complemented by using NAND gate. That is, the NAND gate is the complement of AND gate. So this is the NAND gate. This is Y, so which is equal to AB bar. If this is A and this is B, so it is the complement of NAND gate. So let us see the truth table of the NAND gate. Truth table. So as we already know that how many combinations of combinations we can have in truth table, it is defined as 2 to the power n. Suppose we are taking two output, that is n is the number of input bits. So if we are taking two output, it is we can have 4 combinations. So let us take two inputs, input A and B, and output is Y. So the combinations are 0 0 0 1 1 0 1 1. So it is the complement of AND gate. So which is the logical multiplication. AND gate perform logical multiplication. So 0 0 is 0, but it is complement, so it will be 1. 0 1 is 0, but it will be 1 since it is complement. 1 0 is also 0, but it will be 1. 1 1 is 1, but it will be 0. So this is the truth table for the AND gate. Now let us see the timing diagram. Timing diagram for the AND gate. Let us consider time period as T1, this is T2, this is T3, and this is T4. So timing diagram will be like this. T2, T3, T4. For A it is 0 0 1 1, which is low low high high. So which is low low high high. So it is 0 0 1 1. For B it is 0 1 0 1, which is low high low high. So this low high low high. So it is 0 1 0 1. And for Y, which is the output, it is high 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 low. So it will be high 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 low. So it is 1 1 1 0. So this is all about the NAND gate. Now let us see the XOR gate. XOR gate. So generally XOR gate can also have n number of inputs but have only one output. XOR gate can have n number of input, but all the gates have only one output. So here this is A, this is B, and here Y is equal to A X operator B. Here this sign is the X operator, XOR operator. It is called the XOR operator, which means that A X operator B is A bar B plus B bar A. And this gate only responds for the odd number of ones. This gate only responds for the odd number of ones. And let us see the truth table for this gate in two inputs. Input A and B, and output is Y. So it is 0 0 0 1 1 0 1 1. So putting these values in this equation, we can get 0 0. So it will be 1 into 0 0, it will be 0. So putting this value here, it will be 1. This will also be 1, and this will be 0. So this is the truth table for the XOR gate. This is the truth table for the XOR gate. Now last but not the least, let us see the XNOR gate, which is the XNOR gate. XNOR gate. It is the complement gate for the XOR gate. We can easily say that it is complement gate for the XOR gate, like this. So it is here. It is only not. So if this is a b, so it will be y is equal to a x operator b, will be the complement of x OR gate, and it is also called the even one detector. Since x OR gate is called the odd one detector, it is called even one detector. And let us see the truth table for it. So this will be inputs. We will taking two inputs, a and b, and this is output, which is y. It's 0 0 0 1 1 0 1 1, and see, it is the complement of this. So here y is equal to a bar b plus b bar a, it will be the complement. So putting these values in this equation, we can get 0 0 will be 1, it will be 0 0, this will be 1. So this is all about the logic gates. So I would like to thank everyone for watching this video, and I would like to thank Department of Physics, NAMCHI Government College and Sikkim University, and our teacher Dr. C.P. Khotibata sir for assigning us with various topics. Thank you.